Hello and welcome to this webinar. My name is Fredrik Lagerström and I am the product owner of Prestress and Winstatic, and today I will present post-tension cables in FEM-Design. This is a new webinar series that we will hold, just a couple of webinars during the autumn now with post-tension cables. I will also look at construction stages, and there is also a very high demand for looking at the different results. So we will look forward to those in the near future. But today we will take a look at the agenda for the post-tension cables. I will take a look at where to find them in FEM-Design, and I will also have a live demonstration of how it works. And the live demonstration will be after the webinar. There is a function in the GoToWebinar that is like a raise a hand or something. I will not be able to track that during the webinar, but you may still ask questions, and we will have a questions and answer session after this presentation. The Q&A session will not be recorded, but this webinar will be recorded and will be placed on the Strusoft YouTube channel. So, where do we find these post-tension cables and what are they used for? Well, post-tension cables are for concrete structures, and mostly if it's cast on site, and then you put the post-tension cables in as a mean of reinforcement. They can be found under the bar components for beams, and we will also take a look at the shell components after the bar components here. When you start the post-tension cables, you will come into this settings dialog, and it's a lot of information here. But in order to use this correct, you need to have defined axis for your structure, both along the beam and across the beam. And the same goes for the shells, where you have to have defined axis for the shell. There will be an automatic top and bottom placement for these cables, and the information entered here, well, it is the number of strands, minimum or maximum, and the program will then take this information and apply the best amount that you enter. Be aware of concrete cover and so on. So these wires are quite big and they need to be anchored in the ends. If we take a look at the more in the settings here, we can see that if we have applied the axis correct, then it will automatically generate the curve of the cables along the beam, as we can see here. So it starts in the middle, and then we see that it goes down here, and then over the supports it goes to the top. So in the mid of the span it is further down, and over the supports it is going to the top. And it is this curvature of the pre-stressing cable that will cause uplifting forces in the spans and downwards forces over the supports. These settings are also something that you may change, but always consider to talk to a company that is applying these cables in order for to see what type of cable they have and what kind of jacking setup they have, if it's in the start or in the end, or both start and the end, and what kind of losses that it may cause as well. It is possible to adjust the curvature of the cable. So the initial start may just be that you can see a start point, an end point, or two endpoints, and then inflection places and a base point. So the base point is placed either in the mid of the span or at the top of the support. And it is these inflection places that will be placed basically to say that now the curvature is negative or positive. It is possible to see different kinds of results. One of the main results to look at may be this radius of the curvature in order to see what the cable can be curved, if it may be able to just do, let's say, 20 per meter, or if it's a higher curvature, like here we can see in the right end, then it's a rather curved strand here. So this kind of results will be shown. It's also possible to generate and export the curvature in order for the manufacturing to see what kind of curvature that they need for the placement of the strands. So it's possible to see here at different points where the height in this beam is in that case. If we take a look at the shells, they can be found in the shell components menu. And it's a very similar setup, but in this case, it's defined for shells. So here it is possible to apply it to a shell automatically, rather than if it was just a beam. And here it's possible to also define inflection values, and the post-tension cable layout wizard is basically the same as for the beam. For these different kinds of values, it's possible to look at the layout calculations that is being performed when you press generate. And here the program will display basically the number of cables that it will place over the slab. And if we then take a look at the properties on the auto-generated cables, we get this result similar to the beam. And the results are basically the same. But if we take a look at the short-term losses and the long-term losses, then it is possible to see what kind of losses that we will have. And this is based on the concrete of the slab that we have applied. For the long-term losses, it is important to have the creep and the shrinkage of the slab defined correct. And those will be input values when defining the long-term losses for the pre-stressing cable. The wizard, if we take a look at the properties, well, it is very similar to the beam. So here it is possible to look at the properties of one of the generated strands, and it's possible to define the inflection places and also the placement of the base points in order to get the correct result. Here it's also possible to look at different kinds of results, and we can see the radius result that I've shown here. And in the live presentation, I will show different kinds of results that can be shown here. And similar to the beam, we also have a manufacturing where it's possible to export the points and also possible to edit them here in the manufacturing. All this information, it's possible to add to the documentation in FEM-Design as well. Remember that there will be quite a lot of auto-generated cables and the information might be quite big for the documentation, but it is possible to add it here, and it's just in the bottom left corner of the properties. So what is the loads associated with the post-tension cables? Well, we have the short-term losses and the long-term losses will be loads that will be needed to be added into your load combinations. And since these are auto-generated, they will be named here with blue names, and it's not possible to just remove the load cases from this window. So in order to, if you don't want the loads or the post-tension cables, you need to remove the post-tension cables because these load cases are linked to that object. And if we take a look at the losses and the loads that we will have here, then we will see a jacking force. There will be a moment in the end, and when we have negative curvature, it will be a downwards force, and with the positive curvature, there will be an upwards lifting force instead. And if it's done correct, then this lifting force will reduce the deflection. But in order to get the equilibrium of the pre-stressing force post-tension cables, there needs to be a downwards force, and that is in that case placed over the column. So there will be higher forces in the column and a redistribution of the loads in this case. So if we take a look at the results, what are the main advantages? Well, here I will show two models, one with the post-tension cables and one without the post-tension cables. And the main result and the main accomplishment is that you will have reduced deflections over large spans, and the risk of cracking will also be reduced. There will be a reduction of normal reinforcement, but it's not possible to eliminate the normal reinforcement. You need to have that nonetheless. And it might also be needed some extra reinforcement that is specially linked to the jacking forces in the end and so on, where you have larger forces acting on the structure. And there will still be need for punching reinforcement, shear reinforcement, and minimum reinforcement according to the codes. And here we can see the required normal reinforcement. When I have the post-tension cables, and to the left here, it will be with the post-tension cables, and here it will be just the amount needed for the if we didn't have the post-tension cables. In that case, there will be a much higher reinforcement need over the columns here, for instance. Now I will have a live demonstration. So here we can see a rather big span of the of a structure, and I will need to adjust this a little bit because the span is not correct in this model. So I will place it more in the middle where the columns may be. And there I have a small beam, but here it is possible to have wider beams in order to get more strands into it. And the purpose here is basically to have an outside yard here, and to the right here there will be a structure placed, a 3 or 4 story structure placed. And in order to get the big forces that are acting here, and it might be vehicle loads, it might be more soil, more congregation loads, and so on, that is acting on this structure. And below here, there will be a parking garage, for instance. So we have a ramp down here, and then there will be parking down here below. So you don't want big cracking, don't want big deflections here in the garage, because big deflections might cause cracking, and cracking is not good if it's outside concrete on top here. So we need to apply the post-tension cables here. I will start with the beam. So I select the post-tension cables for bars. Here I have the possibility to enter different values, and I also have the wizard here. The preview is not shown yet because I have not applied it to a beam, so it doesn't really know what beam I'm supposed to have this on yet. It's possible to define it as a straight line, or I can apply it on a line by selection, and in this case it will be the beam. But I will, in this case, start with just a straight line for this beam, and I apply it along the whole beam. And we can now see the curvature of the pre-stressing cable. So it's shown here in blue below the bar. And we can see that since the axes are defined as they are, so I have a top here just above axis 2, axis 3, 4, and 5, and then the cable will be shown here. Now it is possible to look at the information of the cable. Here it's possible to define different kinds of types of cables that can be used. So the default value is a 15.7 cable, millimeter thick cable. And there will be 3 of them here. The jacking is in the start. It's possible to have it in the end, start and then end, or end and then start. So it's possible to define the different place where you will have the jacking, and also the jacking stress is shown here, so you can see and define your post tension or post stressing stress here. Here we have the short-term losses that I've shown before, and yeah, it's according to Eurocode formula 5.44 that we will use for the elastic shortening losses. And as for the long-term losses, well, here it's we need to have the shrinkage and the creep that are input in the long-term losses or the relaxation for the cables. And here it's possible to also see what the calculation results of this big formula is. As for the shape, it is possible to change the position. So if I want the number 3 here, I can place it, let's say, at 7,000. And then it's possible to adjust this, but also the height of the position. So I can basically say that it should be in the mid, top or bottom, or a value of my own. And this will cause the curvature to change, and the loads will be different. In this case, I will place it at the bottom and at 4.8 meters from the end. So if there are problems, like we can see here in the right end, it's possible to maybe raise up this a little bit in order to get the curvature to be a little bit better. If we take a look at the results, I showed the radius of the curvature. Here it's the curvature is rather low here, so it's up here in the end where I have the higher curvature of the strands. The results that we see is, well, different kinds of deviation functions. We have stresses with friction losses, so we can see from what end we had the jacking, and if I would have it differently, then the losses would be different. So here we can see how it is displayed, and if I start it from the right end there, it's possible to see anchorage slip losses along the strand as well, and then my stress losses and what kind of forces that will be applied to the bar here. So this is basically the loads that we can see in the load cases afterwards. As for the manufacturing, it's possible to go in and edit the points here, possible to sort them. I will be able to export it and as a CAD drawing. And also generate points, and I will be able to add it to the documentation, all this information that we've shown here. With this element here, we can go into the loads, and it is possible to see the loads acting here on the beam, and it will be these two blue cables, and then they have to be inserted into a load combination. If I go to the shell instead, I need to go to the shell components, post tension cable for the shell, and I will be able to use the layout wizard and right click here. I will be able to review the information, and I can generate it, and then it will apply my cables. I can say apply. And here we will now see a rather big mesh of the pre-stressing cables. It is possible to review individual cables. So if we take a look at one here in the outer span, we can see the curvature of that one, and we can also see the one here at the closer to the over the supports. And it will try to focus the strands here in strips closer to the axis, where we have the like a strip over the supports or over the column here, and also will be a little bit more focused along the strip here where we have the columns in the other direction as well. If you want to remove a cable that might be thinking, oh, this is too short and this is not really useful, it is possible to do so as well. As for the loads are connected to each pre-stressing strand or post-tension cable, and so the ones I removed here, the loads will also be removed, but for the other cables, they will be still applied here. And I have also a model here, two identical structures where I have post-tension cables in one of them, and I have not post-tension cables in the other. And if I take a look at the analysis results here, we can see that the results for the deflections here are 39, 41, and for the beam about 28, but they are much higher here in the right-hand part. And here I need just normal slack reinforcement in order to reinforce up the moments caused here, but here the moments are less because the way the post-tension cables works. If I go into the reinforcement design, it is possible to see the need for the normal reinforcement on top of the post-tension cables. So here I have the required reinforcement in the bottom in the X direction, which is along the slab here. And it is smaller areas here. And here it's much higher required reinforcement in the bottom. If I take a look at the top in the same direction, then we can see that it's higher here over the columns. And it's basically just half the requirement for normal reinforcement here. But note that you need the post-tension cables here. If I go into the RC bar, I can see and reinforce that bar. And that was unsuccessful. And this was unsuccessful as well because it's too small. So in this case, it might be needed to have a wider beam. And this beam will basically be an underlying beam. So it's not in the same level as we can see here, but it will be lowered. So I might need to define a new beam that is wider, but I still would like the same height of 600. So I will say a new size. The concrete height is 600, but the width might be 1.2 meter. I will use this one. Here we have the material with the creep and shrinkage. I might want to increase the concrete a little bit. And as for the end condition, I want to lower this a little bit. So the slab will be here and it will be sticking out a little bit below the slab here. This will also cause that we can fit more cables into this beam here. I will remove the wire that I have in order to apply more in this beam. And with this kind of structure, it will be much more stiff. The post-tension cables will help with the deflection in the rather long spans. I have 12 meters between the columns here. And since it will become stiffer, of course, it weighs a little bit more, but that will be maybe you have to design the columns in order to take a little bit more force, because there's a rather big area that will go into the columns here. As for the load combinations, we can just see how I have applied it. I have the dead load in the ultimate limit state. I have the live load on top of the slab, and I also included the different kinds of losses in both the ultimate and the serviceability limit state. And this is because there will be need for the stresses and the loads that we can see here in the background to be applied to help with the curvature. I have a rather, I would say, simple model, and I have no nonlinear elements, no plastic, and I have not enabled the cracked section analysis. And the cracked section analysis should only be applied when you have placed the normal reinforcement. So after reinforcement design, then you enable the cracked section analysis, and that will take a look at what kind of deflections we have, how much reinforcement do you have, how high will the stress in the reinforcement be, and then it will calculate the cracking due to that amount of reinforcement that you have. So do not enable the cracked section analysis here in the start until you have performed the reinforced concrete design. And if I don't have the nonlinear elements in the model and it is enabled in the calculation, the calculation will just ignore any nonlinear calculations because there are none. So here it is now possible to see that the deflections over the beam is very small, and the slab itself is not that thick. So I only have a 200 millimeter thick slab, and with 12 meter span, I get very low deflections, and the reinforcement needed is quite low here. Of course, a higher slab will cause more reinforcement because it's a higher dead load, but you will also get better curvature of the strands. So the uplifting forces in the spans will be greater. And still, I have a 12 meter span here, or 10 meter span, and I only have 37 millimeters of deflection with rather high loads. I think I have live load of 4 kilonewtons per square meter. That was taken here from the load surface load generator here. So here I can see the deflections, and since this is a rather quick model, the element mesh is not that very detailed, but you still get rather big differences, and the only difference here is the post-tension cables. And I will be able to take a look at the internal forces that might be interested in the beam. And here we can see that I have a normal force acting on the beam. So this is compressed over the whole length, and that will most likely be that this is uncracked. Here we can see the normal force, the moment in the beam, and the design of the beam will also be the if you add the moment in the beam plus the normal force times the eccentricity of the pre-stressing or post-tension cables here. So this was a quick highlight of the post-tension cables and the information that we have about it here. It is possible to delve deep further into the theory in our theory manuals of FEM-Design. And if I open up the page on the wiki, here there are the theory manual and the verification examples, and also other manuals here that might be interested to read, but it's the theory manual here where it's possible to download it as a PDF as well. So go into the wiki and read more about it. I will now have questions and answers, and for the next FEM-Design highlight webinar, it will be regarding construction stages, and that will be held in 2 weeks. So I will say thank you for attending this webinar, and I hope to see you soon in the construction stages, and also in the other webinars that I will have on Wednesdays.